Good afternoon, everyone. My name is Don Linford. I'm the Director of Innovation Ecosystems here at Aspire. I'd like to welcome you to our April 2024 Tech Talk. Our Tech Talk this month is going to be around our student showcase, where we have several of our talents that are students here at Utah State University and other places, but through Aspire, that are going to be able to talk about their projects and things that they're working on. I know as a center, one of our greatest asset are our students. And obviously it's great for us to have this chance to let them have their moment and to show the things that they're working on. But before we kind of give the time over to them, I would like to go down through just maybe talk about a couple of things. One is some of our center highlights over the last month. One of those is we had at the end of March, a student cohort trip. It was sponsored by our industry innovation member, Kenworth Pakar. Was to the Northwest, and actually Bruno's going to talk a little bit about that, but just want to let know that it was one of the key things. Also, we'd like to call out in the future events that in June, we're planning on doing another cohort. We'd like to do it into the upper Midwest of the United States. And so you will probably see an email from me to some of our members in that region or others to get engaged with that. This is a great trip, and Bruno will talk about it. And we are also participating in One Utah Summit here, and then the APEC Applied Power Electronics Conference and Exposition. What we have coming up is we really want to highlight, besides the student cohort trip in June, we are working towards kind of our big annual event, which is part of our annual meeting. It's our Industry and Innovation Day. It will be held here at Utah State University. This is our, quote, renewal year. This is a year where the National Science Foundation will be coming and looking at us as a center, and we plan on having it here at Utah State University. It's a great opportunity to have folks come in and to network and to mingle. We will have our EVR, our new EVR will be open then. We'll have our inaugural, this will be like our inaugural event for that. We're going to do similar things from last year. So Monday, we expect people to arrive, both NSF as well as our Industry and Innovation Board, our Aspire participants, our faculty, student, staff. That evening, we do plan on having our poster session and a dinner social. It will be here at the EVR. Tuesday, we will have our IIB mini workshops. So some of you industry members, you'll be getting emails or contact from me and soon about that. And then we're doing something a little different. Instead of having a sit-down dinner on Tuesday night, we plan on having a connections reception. We'll send more out about that, but it's going to give our students in industry time for them to be able to go out and meet each other individually. They wanted time maybe to connect beyond our poster session as well as that. So those are the things that we'll be doing. So that's an important event. If you should have gotten a calendar invite, if not, you'll be getting one fairly soon about that. The next thing is the Curve Conference. Even though it's going to be in February 2025, this is one of those conferences where we get a lot of interest and asked about. This is our conference on electrified roadways, and it will be in Park City in February, right after Sundance Film Festival, but it'll be a great skiing time. It's really focused around the industry members, but also people at the policy level. So we're hoping to have as many as possible Department of Transportations and other agency folks there to participate with us. So we're really looking forward to that. So with that, I'd really like to, at this moment, present what we'll be doing today. We will be having our student talent showcase. I'd like to turn now over to Tenzin Laden from UTEP. She will be our moderator, and she'll introduce herself as well as the presenters today. Tenzin, please take it away.
Thank you, Don. Let me share my screen. Good afternoon, everyone. My name is Tenzin, and I am a member of the Aspire Student Leadership Council from UTEP. And I will be the moderator for today. So once again, welcome to the Aspire Tech Talk series. And this session today's session will be based on Student Talent Showcase. Now, as usual, this will be an hour-long session. I will be giving a quick introduction for all the participants. And we will first have a short 10 minutes presentation and 20 minutes each for the remaining two. Now, let me start with the short introduction, starting with myself. My name is Tenzin Thaden. I'm a master's student here in UTEP studying industrial engineering, and I am a research assistant to Dr. Bill Seng, and my current project is about smart charging management algorithm. And about my past education, I did my Bachelor's of Technology in Mechanical Engineering from Sharda University, India. Now, our first presenter will be Bruno Cesar Coras Moraz from Purdue University. He's a PhD student of civil engineering, and then he will be presenting, he will be giving a short overview of the recent SLC cohort trip that we had in Seattle. And I must say, I was quite fortunate to be a part of that trip, and it was really a good exposure for me. Now, to talk more about Bruno, his current projects are about sustainable transportation systems, focusing mostly on statistical analysis of public perceptions of electric vehicles and their adoption and charging stations. Bruno got his bachelor's degree in civil engineering from the Federal University of Technology in Paraná, Brazil, and his master's degree from the Polytechnic Institute of Bragança, Portugal. Now, to talk more about Bruno, he's currently a mentor for undergraduate researchers, and also he has experience as a mathematical instructor for more than 1,000 high school students. Now, our second presenter will be Abdullah Zubair Mohammed. He is a PhD student of electrical and computer engineering from Virginia Tech. He will be presenting one of his projects on distinguishing vehicles through wireless fingerprinting. His current projects are cyber physical systems security, embedded systems security, and device fingerprinting. To talk about his past education, he got his master's degree from the Indian Institute of Technology, Hyderabad, in India. And also, I must say, as an engineering student myself, I have always been a big fan of IIT, and it's finally exciting to meet someone who graduated from there. So to talk more about Abdullah, he was a design engineer at the baseband team at Silicon Labs. Our final presenter will be Pedram Baluch Srigani. He is currently a PhD student in civil engineering from here in University of Texas at El Paso. His presentation topic will be about reduction of temperature sensitivity of pavement for safe and durable electrified roadways. And his current project is based on analyzing temperature distribution and viscoelastic behavior in asphalt pavement design for electrified roadways. Now, his past education, he got his Master's of Science in Road and Transportation Engineering from University of Guilan in Iran in 2018. Now, before we start the presentation, I would like to say we will have a short Q&A session between each presentations, and otherwise you can also drop your questions in the comment section. Sorry, not, I mean the chat box. So, okay, Bruno, you can start.
Okay. Thank you, Tenzin. I would like to say that I'm really happy to be sharing the highlights of the Aspire cohort trip of March in Seattle. Before we starting speaking about this trip, I just would like to give an overview about the cohort program. That is an opportunity that Aspire gives to the Student Leadership Council members, and in this trip too, to the ASA members, to visit some partner universities, national labs, and offices from industry and innovation partners. In this case, in this trip, we went to Kenworth and PACCAR, and it was an amazing opportunity. Today, now, what I will be talking is more the highlights of the trip. We also do a SWOT analysis that won't be presented today, but in the future. And more than just having the visits, we also have mentorship. We also have very special people with us. In this trip specifically, we have Brian that worked in Kenworth, and also Professor Brandon, Ellen, Jennifer, and Melanie. Melanie was in her first day of work at Aspire. It was in 50 years in the future. She'll be able to tell that in her first day of Aspire, she was with us. Okay, so now about the trip, about our visits. I speak about some of the places that we went, specifically Kenworth, Packard, Washington State Ferries, Amazon, Lewis County Transit, TransAlta, and Centralia College. And how it was? Well, the first place that we visit, it was Kenworth, that is an industry innovation member of Aspire. Kenworth is a company that produces, manufactures trucks. It's a traditional company in the United States, and now is also producing electric trucks. It was an amazing opportunity to see the facilities there. We were together with Brian and Ryan, the director of research of Kenworth, and we could see from the first point of a truck being built until the end. Also there, we could see some of the challenges that the electrification of trucks have. Also some projects. Unhappily, we could not share the photos of some of the projects. They are designing a very, and I use this word, futuristic truck that you could see. We could ask questions. It was a really nice opportunity to learn more about the truck electrification. Also, we went in Packard facilities, and Packard, let's say Kenworth is under the umbrella of Packard. Packard is a global technology leader in the truck service, including charging solutions and infrastructure. In Packard, we had the opportunity to, besides visiting the facilities and the equipment, to have a question and answer section with the company technical team, when we really enjoyed the opportunity to make questions to them, and we really appreciate the time that we had to speaking with them. We noticed that some of the people there really stopped to work to talk with us for 1 hour. And this is, I think this is really valuable. If you think that you stop 1 hour of your day to answer other people's questions, to give some attention, to explain some of the process, and the way that they did, it was amazing. Besides these two, we went to Washington State Ferries. The Washington State Ferries now have a plan to converting the ferry system to electric and hybrid until 2040. We talked about the procedures, about the plan, and also we went in Amazon. Seattle is one of the places where Amazon has a lot of offices. And Amazon has a big fleet of electric vehicles, but not just electric vehicles. They are planning to have a very sustainable transportation for the deliveries, including electrification. So we could talk about not just the electrification of the vehicles, but all of the system and how the electrification is included on that. And now I would really like to highlight this transition. We went to Amazon, the giant of the e-commerce that's known in all of the world, but also we went to Lewis County Transit. Lewis County is a county with less than 100,000 inhabitants, 81,000 approximately. So we went from the giant of the e-commerce to a small county in the state of Washington. And there we also could see some of the challenges that they have. They started to implement bus electrifications in their fleet, but they start to have some problems. And it was really amazing to understand what were the problems. Sometimes we think in big problems, but we could see some small problems that are still problems, that it still not allow the electrification of the fleet in a very good way. For example, they had problems with the service, with people who should give a better assistance to them, to explaining about the induction charging stations. The company who they hired didn't make well, and they were, let's say, evaluating the electrification of the fleet by the overall experience. Sometimes we think about electrification in the big companies, in the big cities, but we also have to think in small cities, in small companies, small institutions. Another transition now is this photo here in the bottom right, where we saw some really big machines. In this case, it was the first mode providing grounds that test and optimize next generation of zero emission ultra class haul trucks. We made a question and answer session. We could see some of the machines. It was a really valuable experience. Besides these visits, we also went to the Centralia College for a talk, and we have some reflections with Professor Brandon Allen about diversity and inclusion in Aspire and in general in the electrification vehicle world, and also with Jennifer about the environmental sustainability. Again, it was a really valuable experience. Finally, I would like to say thank you for everyone who is listening, and especially everyone who was with us in the trip. Professor Brandon Allen, Brian was a really nice, really mentor. Jennifer, Melanie, Ryan, who helped us in the trip, all the companies, institutions, and partners who helped us. And I'd like just to finish with this slide that is famous in Aspire. And I think it tells a lot about what was this trip, because in this image, we have some machines extracting resources in the left, we have a truck in the middle, we have bus in the middle, we have transportation of passengers in the right. It shows a really holistic transportation, a really holistic electrification of the transportation modes. And it was exactly what happened in this trip. We had the opportunity to see the TransAlta with machines to extract the components, and these machines are becoming electric. We could see Kenworth with the truck electrification. We could see Lewis County with the buses that they are trying to transform to electric. So it was a really holistic trip. And this reminds me the Aspire vision that said, widespread of all vehicle class, widespread electrification of all vehicle class. So it was a really good opportunity to talk with the colleagues, because sometimes when you are studying, researching something, we are really focused in one single part of a research of a problem, that's electrification of the vehicles. But this trip, at least for me, but I'm sure for the other SLC members, would provide a big picture of the electrification of vehicles. And for this reason, it was an amazing opportunity. Thank you.
Thank you, Bruno. That was exactly 10 minutes. Now we'll have Abdullah to present.
Thank you, Tenzin, for the introduction. Good afternoon, everybody. I will be presenting my my research on the project of wireless vehicle fingerprinting, which I'm doing with my advisor, Dr. Ryan Gerdes, here at Virginia Tech. To start with, in this context, vehicle fingerprinting means to identify the make, model, and year of a particular vehicle. So we begin with the motivation to do so. why is there a need from a security perspective, from a cyber physical system security perspective, to identify the vehicles, the make, model, and year. So we go over multiple threats, starting with the threat of overcharging a plug-in electric vehicle. In this, we assume that the adversary has compromised, has gained a foothold in the EV, and has particularly compromised a battery management system, a type of CPS in an electric vehicle. And once it has done so, it can tamper with parameters such as the limit for the cutoff voltage or the cutoff temperature, and cause the battery to overcharge while it is being charged by the charging station. And persistent overcharging to lithium-ion batteries, in most of the cases, it may damage the health of the battery. And in some cases, if it is persistent enough, the battery can enter thermal runaway, and the temperature keeps on increasing, which may even lead to combustion or explosion of the battery. A similar threat, which I think is more relatable here, is in wireless power transfer, both static and dynamic. A similar threat of a compromised BMS leading to overcharging exists. And also another threat that exists here is if the adversary can introduce a metal object under the vehicle at the receiver of the power. And we know that with the kilowatts of power that goes into WPD, strong EM fields interacting with the conductor could lead, could create strong radiation that can impact both organic matter around, like even the driver or the passengers, and the other matter around, other objects around the vehicle. So there is a need, if the transmitter identifies that this undercarriage does not belong to an EV, and so it does not grant the charging request. And another threat in the intelligent transport system infrastructure, where in this case it's an unmanned vehicle access control to restricted areas, and the adversary has stolen the identifier. It can be RFID or any other digital identifier, or even the license plate of the vehicle, and is attempting to gain access by presenting itself as a registered vehicle. And the impersonation threat while the vehicle is mobile. For example, in this case, it can use replay attacks to bypass the communication between, let's say, a mobile emergency vehicle and the traffic system, automatic traffic system, to gain access to, let's say, green lights on the road. So therefore, if the intelligent transport system identifies the make, model, and year, that would help in convincing that this make and model does not appear to be of an EMV or a registered vehicle, and it adds a layer of security to grant access. So the first sensor that comes to mind for all of us when we would like to recognize vehicle are the cameras, the surveillance and the traffic cameras, but they have their challenges of their own. Few of them are listed here. For example, viewpoint changes. The car may be facing different directions. There may be a problem of illumination, night and day. The performance may vary. There may be weather conditions. The weather may be foggy, or it may be raining, that could impact the accuracy, or the vehicle may be there may be an occlusion from any other object around it. And in addition to this, there are in the recent literature, there has been attacks which can simply introduce a patch in front of the camera and fail the classification of the vehicle. Therefore, what we propose is a fingerprinting technique through already widely deployed infrastructure of inductive loop detectors that we find it everywhere around us. If you look at on the roadways around us, more at the traffic intersections, we see that an inductive loop already exists. And in the current infrastructure, it is used only to detect that a vehicle is over it. And we would like to use this to identify vehicles also, so that may strengthen the security. It can be on its own or be a complementary approach to cameras, since their vulnerabilities are orthogonal and they can work together to improve the security. In the current state of art, the techniques using ILD do exist, but they mostly classify the vehicles based on into a limited number of classes based on their body type. If it's a motorcycle or a smaller car or a bigger car or a truck, so on and so forth. What we aim to do is to have a fine-grained classification and to identify each make, model, and year of the vehicle that passes over or stops on the inductive loop. A brief theory before we move on to the proposed technique. Essentially, inductive loop is a magnetic loop buried under the ground, and there is an electronic housing unit nearby which provides it with a time varying excitation current. This current generates a magnetic field which hits the undercarriage of the vehicle when it comes over it, and when it does so, it produces currents called as eddy currents on the undercarriage of the vehicle. This eddy currents, in turn, they produce another magnetic field, PE, which opposes the original magnetic field. And these changes are detected by the housing unit to say that there is the vehicle is over the loop. Now, what makes fingerprinting possible is that BE is vehicle specific. Every vehicle has their own different undercarriage, different metal content, different geometry, different ground clearance, and so on and so forth. So these changes in BE can be used to identify the vehicle that is over the loop. To do so, instead of the single tone signal, a sinusoidal signal that the conventional ILDs use, we propose to use a wideband signal so that a wide range of frequency can capture this unique features, multiple unique features of each vehicle and help in classification. So methodology of our approach was to firstly select the kind of wideband signal we are going to use. And based on that, we designed the hardware that could generate the excitation current, which includes an amplifier. And then with the created hardware and a prototype, we acquire data from vehicles and train our model so that we can perform analysis over it and classify vehicles. Briefly, for our excitation signal, we used a quadrature amplitude modulation for multiple reasons. It was simpler to generate when compared to other complex wideband signals such as OFDM, and we selected a frequency range that was comparable to the conventional ILD detector, so that it becomes easier to integrate with the existing hardware. And also, if we go at higher frequencies, the impedance of the loop increases, which would want us to produce a larger amount of current, and that would require more power. And also, lastly, the near field effect at these frequencies are at a comfortable height, so that the field generated can impact the undercarriage of the vehicle at a reasonable input power. And in our lab, in the prototype, we were able to generate this signal using a software-defined radio, USRP and 210, with a couple of RF daughter cards. Subsequently, a schematic was designed and a hardware was developed, and a prototype was developed so that we can proceed with acquiring data to train our model. What followed was an extensive data acquisition from the vehicles in our building, and also from a nearby car dealership, that we acquire data from different vehicles, different types of vehicles, gas vehicles, electric, and also hybrid, and also this over a period of 9 months, so that we can account for two things. First is temporal variation of our fingerprint. Ideally, fingerprint should not change over time, and we wanted to verify that. And also, it should not change based on the changes in the environment, and therefore the ambient temperature, the outside temperature range from 0 degrees to 35 degrees centigrade for our data acquisition. Data was acquired from by sliding the loop under the front, center, and rear of the vehicle. We will discuss in the further slides why was there a need to do so. We started with data analysis with a simpler statistical analysis, basically calculated the standard deviation, and the performance of this particular analysis depended on the number of samples that we have. For smaller number of samples, there wasn't any differentiation. For more, there was, but the model still was not able to distinguish between vehicles of same body type. So therefore, we felt it necessary that we need to move towards a deep learning a neural network, essentially a convolutional neural network, CNN, the input to which was the data from all the three sides, positions of the vehicle converted to frequency domain. And after the convolutional layer, and there were a couple of fully connected layers followed by a classifier, essentially a softmax layer that could classify the vehicles. For our analysis, we still wanted to show that our model can do body type as well, like the existing techniques do, and which was carried out in two scenarios. The simpler closed world, where we have in our testing, we have all the vehicles that exist. In training, we have all the vehicles that exist in testing, and in open world, there are different vehicles for training and testing. And of course, what we aimed for was make, model, and year classification. We did that for k-fold analysis, and also, like I said, temporal to check the temporal variation of the fingerprint. We trained from the data from 1 month and tested on the data from a couple of months later to see that if we could still classify. These are the results for the body type classification. We started with having just one position of data, but once we moved to two positions, the results started improving. This is a confusion matrix, and we see that for two positions in a closed world, we could achieve up to 96% of accuracy on identifying the vehicle is either a truck or a minivan or a sedan or an SUV. Open world, as expected, was a difficult problem because the model will be seeing different types of sedans it wasn't trained on, so the accuracy decreased, but we still had decent accuracy, and it is not very impractical for this particular application to have a closed world training, since at a given time there are limited number of vehicles that exist, limited vehicles of models that exist. And finally, the classification with for make, model, and year, we were able to test for 25 different vehicles, and the accuracy kept on improving if we included data from all the three positions, and we were able to see an 89% of accuracy in classifying this vehicles. Then, as it is apparent here, there was an outlier because of the trucks here, and there were a couple of reasons for that. One was that 3 of the 4 trucks that we acquired data from, they belong to same make, GMC, and so what we believe is that they are made of similar material, and essentially they may be using the same chassis for a different model of vehicles. So there was some confusion in classifying that, and also trucks sit at a higher ground clearance, so maybe the power was not enough to impact the undercarriage of the vehicle. To solve this problem, it is kind of a future work that we improve the power, we increase the power of the excitation signal so that it can do both extract features even if the chassis is of the similar make, and also have a higher power that can reach a slightly longer height. But if we removed one of the trucks from the data, the accuracy jumped to 93%. Finally, we'll discuss the practical scenarios. First is we tested it over 3 different positions. This is practical because if we look at the practical loops on our highways, on our roadways, we see that those are bigger in size than what we had in our prototype, and also there are adjacent loops placed to capture the complete undercarriage of the vehicle. So to get data from the entire vehicle is not impractical, and that is highly practical to do so. And most of our testing was done on the vehicles that were parked. But theoretically, based on the duration of data that it requires for our model to take a decision, we can theoretically classify vehicles that can have a maximum speed of 90 kilometers per hour. Of course, it's a future work to do experiments on the vehicle that is actually mobile. And lastly, we also tested if we can classify, we can separate vehicles of same make, model, and year. As you can see here, if for a Honda Civic of 2002 and 2008, there was decent accuracy, similar for Accord if they were separated by so many years. But as the vehicles were becoming more and more identical, for example, Sienna of 2021 and 2022, the accuracy dropped because those are essentially the same vehicles. And if in the last case of Buick and Vision of same make, model, and year, and these two vehicles were from the dealership, so practically new vehicles, so no changes by the usage. So therefore, these were identical vehicles, and we were not able to classify that. This is again a part of future work, so that if we can come up with signals, different type of wideband signals, and at higher power to extract. Because essentially manufacturing imperfections will be there even if the vehicles are of same make, model, and year. And if we can come up with some signal and some power to extract this. That's all I had, and thank you for giving me the opportunity to present this work. I'll be happy to answer any questions.
Do we have any questions for Abdullah? Okay, I don't think we have
I
any
have one
questions.
question.
Oh, sorry. Yes.
So I guess I'm not as familiar with these already installed coils. How like widely deployed are these coils currently? Like I understand the stoplights, they have them. Like across the nation, is this pretty common like everywhere? Or would some of these vehicle detectors need to be installed in new places around the country?
Oh, vehicle detectors are pretty common in the current infrastructure. It has been for many decades. In fact, a single county in Maryland has 10,000 inductive loop detectors installed on the roadways. So we just propose to use them not just for detecting, but also for identifying vehicles.
Do we have any more questions? You are free to drop your questions in the chat box later on. I think we'll move on to Pedro. Thank you so much, Abdullah, for your
Thank
for your
you.
time.
Thank you, Tanzeen.
Pedro?
Good afternoon, everyone. Please let me share the screen. So now, can you see my screen?
Yes.
Okay. So today I'm going to discuss the reduction of temperature sensitivity of pavements for safe and durable electrical roadways. As you know, using charging unit in asphalt pavements generates waste heat, which increases the temperature within the asphalt pavements. So our objectives in this study is to develop a validated finite element model to predict this temperature increase based on our experimental results from the lab. So, and also after that, we are going to explore the different materials to decrease the temperature sensitivity of asphalt mixes and improve their performance. So you can see here our experimental steps. The first step is temperature distribution analysis that I will discuss next slide. So, and the second step is viscoelastic behavior assessment, which is really important property for us for prediction of temperature increase inside the asphalt pavements. And finally, we will have MLS machine to evaluate the performance of asphalt pavements with different materials under loading, included embedded charging units. Here we can see our experimental plan for both PG64 -22, which is conventional polymer that we are using in Texas, and also polymer modified PG88 -28 that we expect to have better performance in higher temperatures. As you can see here in the table, we have considered 3 different locations for heating pad, which simulate the charging unit system. We're using heating pad in this study in different depths. For example, here 115 is in the bottom of the samples, and also we put heating pad in 75, 57, and also 40, which is correspond to 2/3 middle and also 1/3 of height of the sample respectively. And also we have considered for different temperature for heating pad, 15, 60, 80, and 100 centigrade, and as well as for different ambient temperature, which are 10, 25, 30, 40 centigrade. Here we can see our experimental setup for small samples. As you can see, we put the heating pad in the middle of the sample for this case. And after that, we have tried to, based on heat transfer theory, which is convection, radiation, and conduction, simulate the condition of our sample in the lab in finite element software. As you can see here, it's include asphalt mixture, heating pad, and also a styrofoam for installation. So here is our steps for finite element modeling. In the first step, we analyze the sample without heating pad, and after that, we also analyze the sample with heating pad inside, and at the end, we're going to develop the load model of asphalt pavements, including the embedded charging unit. Here, you can see we have tried to consider different conditions to compare the experimental and predicted results. We have used RMSE, root mean square error to calculate the correlation between our experimental and predicted results. We have considered different conditions. You can see here 6 cases, different condition of heat pad location, thermocouple location, and also different ambient temperature, which is set in 60 centigrade for heat pad temperature. And here, as you may know, there are 2 more important parameters for us for thermal analysis of asphalt mixes, which are thermal conductivity and also a specific heat capacity. As you can see here, changing a specific heat capacity did not significantly affect RMSE. However, for thermal conductivity, when thermal conductivity is changing. We can see significant change in our RMSE results. So based on these figures, we have decided to only change thermal conductivity to obtain the optimal value for thermal conductivity, because it was difficult to measure the thermal conductivity of asphalt mixture directly. So we use this approach to obtain our thermal conductivity value. Here you can see one example on our work here. It's for case 4 that we considered a specific heat capacity 100 for all cases, but we have changed thermal conductivity between 7.7 to 1.8, showing the practical range of thermal conductivity of asphalt sample based on prior studies. So as you can see in the left side, this is our optimal thermal conductivity 1.5, which shows the lowest RMSE for all cases. Here you can see the most of the cases are the RMSE of most of the cases are below 5%, which is our goal, to keep it below the 5%. But for 2 cases, it's close to 5. It's about 5.46 that you can see here. This is our example plot for a different location of thermocouples. For example, here we have 4 hours heating, the red curve, and 4 hours cooling, the blue curve. We have tried to formulate and characterize this temperature profile based on its make it easier for us to formulate our temperature profile. So there are 3 important parameters in S-shaped curve, which is L, which corresponds to the maximum temperature of the sample after 4 hours heating here, and also K, steepness, and X0, midpoint. As you can see here, for one case, we plotted the fitted logistic function for experimental result, and we compared this result with FE result. You can see the result are closely matched. The RMSE is 1.35, which is below 5%. That is our goal, and also the good correlation between predicted temperature and experimental temperature is also evident here in the quality plot of experimental versus predicted temperature. Here, we also try to compare the temperature profile of modified sample, which is PG64-22 to polymer modified asphalt. As you can see, the thermocouples readings shows similar result, which suggested that our results. But in other steps that I mentioned before, viscoelastic behavior and also rotting resistant and cracking resistant under the loading, we expect that polymer modified asphalt samples shows better performance. And here you can see a summary table of for different condition for both types of asphalt mixes. So we're going to complete it, and after that we can compare the LKX for PG64-22 with LKX with polymer modified samples. And at the end, these are our upcoming tasks for next steps, which is determination of the dynamic modulus of asphalt mixture. We are working on it now. We are using an asphalt mixture performance tester AMPT machine to determine the dynamic modulus, which is one of the important property and characteristic of asphalt mixes in our field can predict the performance of the sample in high temperatures. And also, fortunately, we now have MLS machine in our lab. It's almost ready to work, so we can work on big scale samples and use actual loading when the asphalt payments with asphalt payment included embedded charging units. So after that, we can analyze the strain and also the temperature in different location of our big samples. And at the end, we can have our last goal, which is have optimal materials and also mixed design for long-term durability of electrical pavements. Thank you very much. Do you have any question?
We have about 6 minutes before we end the session. So do we have any questions for any of the speakers today?
I'll jump in with a question on, so when it comes to the range of dynamic temperature, what kind of range are you planning to test?
It's between 50 to 100.
So what do you do about the temperatures that are outside that range? Since obviously, right, the temperatures can go below freezing, but also can be quite a bit higher than 100 degrees. I assume we're talking Fahrenheit.
No, I'm talking about centigrade. It's all
Oh,
centigrade.
okay. So, but
Yeah, it's awesome.
so you're only paying attention to the very high temperatures, 50 centigrade to, okay.
Yeah, because we already have a lot of work in different temperature asphalt samples, but now we are focused on the extra heat that generates by charging units. So this is the important parameter.
So you're not worried about the way that the
us in
ambient
this
temperature
project.
affects the system. You're just worried about the temperature that from its heating.
Yes.
Okay,
We must only care about the asphalt pavements.
gotcha. Thanks.
Thank you. Any other question?
Curiosity, what finite element analysis tool did you use for modeling?
It's thermal transient theory, heat transfer theory. It's based on heat transfer theory, which also called thermal transient method.
Hello, Pedro. I'm Doug Wilson from the University of Auckland, New Zealand. Very interesting presentation. Thank you. And just a question in regards to the temperature. You said 50 to 100 degrees Celsius. Does that mean that's the heat generated from your element, not necessarily what's in the asphalt? So that's the range you're doing for the heating element. Is that right?
Right. Yeah, you can see
Yeah.
here. I can show you in our experimental plan. This is the temperature we set for our heating pad temperature for heating.
Right. I can't quite see the. My screen is quite small, so I can't see the in the table there. But yeah.
Yeah, it's 50, 60, 80, and 100 because
Okay.
we don't
That's
know
the
the
heating.
yeah
heating element. Yeah. Okay. So what is the temperature that you're measuring in the asphalt, say a couple of centimeters away from the actual heating element?
Sorry, I couldn't hear you well.
I'm just wondering what is the temperature that you're actually predicting or have seen in the asphalt adjacent to the heating element? Say a couple of centimeters away.
Yeah, so we have used 5 different thermocouples in different location of our samples.
Mhm.
We set, for example, 60, 80 in heating pad, and we measure the different location of the samples. For example, here we have this. You can see it's for different location. Here is the surface. Here is -25.
Right.
Depths of the far from the surface.
Okay. Yeah.
And also we put the thermocouples close attached to heating pad to control the temperature of the heating pad.
Thank you.
Thank you. Thank you very much.
Any last question?
Maybe one further question, Pedram. The MLS 11 is the way the accelerated pavement test facility that you're going to be using, isn't it, at UTEP? Is that right?
Right.
And what temperature range does the MLS 11 allow you to the ambient temperature within the chamber?
Honestly, right now, I don't know. I should check it because it's almost ready. So I didn't check it, which temperature we can perform our test.
Okay.
But it has temperature chamber, so I think we can do it in a different temperature.
Mhm. Okay.
Well, we have 1 minute before we end the session. It was a good interaction. Thank you everyone for attending this session today, and thank you to all the presenters. And also thank you, Dawn, Luciana, and Connor for your guidance. And I think I'll pass on to you, Dawn, now.
Like to thank the students for their presentation and for everyone participating. We'll have a recording of this session will be made available for those who are interested and also through our website. And we look forward to you at our next Tech Talk. Thank you, everyone. Have a good afternoon.